Did I give you 11th of July?
Next.
Can I just say why x and y residual are calculated from x?
Huh? Hang on a second.
From using x.
Hang on, what's going on? I don't know. Whatever date I put on it, that's whatever it is. You've lots of time. Lots of time. Okay, let's continue. Are you going to sit down, Mookie? Why not?
But lots of time doesn't mean the quality is high.
Is South Korea in the World Cup still, or are they out yet?
Not yet.
Not yet. Soon. Okay,
Yeah.
soon.
Maybe.
Right. Oh, Saudi's playing Egypt today, aren't they?
I thought they're out.
Oh, yeah.
All of them are out.
Who don't have a chance to win? Saudi and Egypt? They've no chance. It's impossible now. Okay. Is this not on? Beach. No. Come on. There we go. All right. Yeah, I don't actually have this here. Okay, so we're continuing. There's a tiny bit left to do from the last lesson. We spent a good bit talking about fission and fuel rods and moderator materials and control rods and the dangers, and this is all. That was all about nuclear fission. Now we're going to have a look at a different process called nuclear fusion. So if you can write this down as an example, this is H2 and this is H3, hydrogen 2 and hydrogen 3, and they come together and they produce a helium, a neutron and some energy. So we'll write this equation down now. Yeah. Well, let's actually write the equation down. So you've got H2 as an example. How many protons in H2? 1. Plus H3. And that becomes helium, your alpha particle, plus a neutron, plus some energy. And I have the picture here. So you have your H2 and your H3, and they smash together, and then they become H4, a neutron, and some energy. And the H4 goes off, the neutron goes off, and the energy comes out. So this is called fusion. Because I think I said this last time, what does the verb fuse mean?
Fuse.
Yeah, like stick, combine, stuck together. Yeah.
It means fusion release energy.
Yeah?
Then fission release energy.
Yeah. Everything releases energy.
Everything releases energy.
Wow. Every process we were looking at, yeah.
Fission is bigger.
Huh?
Fission is bigger.
Probably the fission.
Fission?
Probably. No, what am I saying? I'm nearly 100% sure it's the fission, because you can do so much to make the fission even stronger. Yeah. Okay. Do you have this? Yeah. So this process is safe because you can see here there's no chain reaction. Can you see that? Because Here you have H2 and H3, and it becomes H4, and there's no more H2 and H3, so the process can't continue. So the question then is, how do you get the H2 and the H3 to stick together to make the helium and the energy? So before we look at that, just a definition here. Oh, by the way, hydrogen 2 is an isotope. Hydrogen 3 is an isotope of hydrogen. And these isotopes have names, and I don't know if you know this from chemistry. So hydrogen 2 is called deuterium. You don't use this word in chemistry? No. And hydrogen 3, tritium. Huh? You don't need to know that, but you know, in the question they might say, below is an equation for deuterium and tritium, and they might give the equation and they might ask you to balance it. You don't need to know it. It's just good to at least see these words. Yeah. So you don't use a special word for H2 or H3 in chemistry then. Okay, continue. Yeah, so the formal definition of fusion now. So nuclear fusion is the process of making a single heavy nucleus from two lighter nuclei. So in other words, in this picture, you made this heavy nucleus from using these two lighter nucleus. Can you see how that's the opposite of fission? What's the fission? Fission is you make two light nuclei from one heavy nuclei, whereas the fusion is literally the opposite. You take a heavy nucleus, you make a heavy nucleus from two light nuclei. This process is called the nuclear reaction as well, and it releases a large amount of energy. And yes, Way, the first sentence is enough for the exam. Yeah? Now I don't have a picture, but I need to draw it for you, because the picture I wanted is in my old physics book from high school. I'll have to scan it and do things to get it, so I'll just draw it easier. So we've seen the fission reactor with the control rods and the moderator materials and all that type of stuff. And what's the most dangerous or the weakest part of the fission reactor? Which part? Yeah, for the control rods. Yeah, because if the control rods get stuck, what can happen? Remember? Yeah, overheats. Yeah. Okay, so let's look at how we could make a fusion reactor. Bruce, you just need the first sentence is enough. Yeah. Okay, so the first thing is, how can we get the H2 and the H3 to stick together? Because what charge is the H2 in the picture? If I go back to the picture here, what charge is H2 here? Positive. And H3? Positive. There's no electrons in this picture, okay? So how can I get those two to stick together? Well, they need to get really, really close, and then they'll stick. Because of which force? The strong nuclear force, isn't it? And what distance are we talking about? How close is close?
10 to the minus
5.
Oh, I think it's much smaller than 5. But
15.
15, I think. 15. So how could we get these two atoms that close together? What could we do? Well, you might think one thing we can do is just fire them at each other. But there's a little problem with that. What happens is, when they fire at each other, because of their positive charge, they'll repel and then they scatter. So they can't really go in a straight line. So we need to try something else then. Okay, so this is the idea. First you start off if you want to think of the process, it starts off like this. You have a gas of H2 and H3, okay, but this is positive. And you know from the right-hand rule, if you have a magnetic field, you can make a force on the positive charge. You remember the formula F equals QVB? Yeah? So if the Q and the V and the B, they follow the right-hand rule. So you can make a force. Anyway, the point is, if I put a magnet around this, I could make a force around it. Whoa, that's not a magnet. North, and south. So what they do is they make this kind of a dome, a sphere. I'll leave a little gap here. And this is basically just, it's lots and lots and lots of magnets. Lots of them. So the magnets make the gas turn into this shape. So this is the gas here. And these are magnets all around the outside. Okay, so you really try to keep the gas like as a ball. Okay, and this space here is just empty. It's okay so far? Yep. Okay, so then the next thing you do, you put around the gas some lithium gas. And then the next thing you do is you use little lasers around the edge here. So these lasers fire into the lithium and into the center, and they all meet at the center of the gas here. So what will happen to this gas when the lasers hit it? Well, it'll get hot, right? So more and more lasers, more and more energy, the gas will get hotter and hotter. What's happening to the H2 and the H3 particles inside the gas as it gets hotter? It excites them, yeah. So they're moving around faster and faster. So if you get them fast enough, when they collide, they stick together. And then what will happen?
Burning.
They turn, fusion. Then they turn into helium and they release energy. Okay? So then the energy comes out as heat. So then what you have then is you have a pipe that goes in. Woohoo. And the reason for the lithium here is so that the pipe doesn't melt. Okay, but the lithium is a bit like what was it in the fission, the sodium, wasn't it? It acts as a way to take the heat away from the center and not to melt the pipe. So of course the cold water goes in here, and what comes out here is steam, and the steam turns the turbine and makes the power. So the problem with this process is you need a lot of energy to go into it, because you have to have all the lasers, okay? So let's say some energy E is used for the lasers. The good news is you do get more energy out than what you have to put into the machine, okay? The energy that comes out in the form of steam and heat will be about 10 E. So basically this process takes some hydrogen, takes hydrogen 2, hydrogen 3, heats it up, makes the fusion, you put in some energy in the lasers, and out comes more energy than what you put in. And it doesn't break the conservation of energy, because where did the extra 9E come from? Where did that 9E come from? Yeah, from the fusion, when the mass was lost, when they became helium then. This process should remind you of something. You have a giant gas that's really hot and releases a lot of energy. Anybody know what this could be? I'll give you a clue. You feel it a lot today. So yeah, the sun is a gas of hydrogen, and it's slowly turning into helium and releasing energy. Now, the difference with the sun though is here we need to heat the gas to make the fusion. Obviously there's no lasers pointing into the sun, so how is the sun able to fuse the atoms together if there's no process to fuse it? What is the sun doing to fuse the atoms together? Does anybody know how it can fuse the atoms together? Any ideas? No? No ideas? The sun's gravity is strong enough that when it pulls the atoms into its center, the atoms fuse together, they turn into heat and helium, and the energy is released then. So it's because the sun is big enough, it can pull the atoms in and fuse them together like this. Yeah. So in fact, the fusion reactor is literally like a mini sun. You make a mini sun, and that's how you make energy from fusion. And what's wonderful is it's 100% clean. Because the only thing that comes out at the end is helium. Which of course is a naturally occurring atom that you use in balloons.
Why don't people use this?
Yeah, why don't people use this one? Because keeping this process going is very difficult because it's very hard to contain the gas, and once the gas collapses, you can't continue the process because you need to keep it compact as a sphere. So I think the current time, I believe, is approximately 2 seconds, and then it collapses.
Oh, 2 seconds.
Yeah, you need your power plant running for more than 2 seconds, obviously. But it's a start, and this is 100% clean, which, you know, maybe 50 years, maybe 100 years, all the power plants will be replaced by this one. So 100% clean. You know, it releases no waste, just helium, no radioactive waste, no risk of explosion. It's very, very safe. In fact, it's safer than oil or gas, because you know what happens with oil and gas. They sometimes explode in your fires. You know, you don't even have that with this. So perhaps one day in the future these will become more common, but at the moment there are 0 power plants that use this. So what I'd like you to do is to try and copy this wonderful picture in your notebook, and if you can't see what a part is, I can tell you. So just to recap, this is in the middle here is H2 and H3. Out here is lithium. This is just empty. Well, more or less empty. I suppose the lithium would fill it up. And this is cold water goes in and steam comes out. And there's magnets all around the outside of it. It's all around it.
The energy, we get the energy in form of steam.
Yeah, it comes out from the reactor as steam.
So we don't have a generator.
Oh yeah, well, I didn't draw the full picture. Yeah, you're right. Like this would be connected to the AC generator. Yeah. Steam to AC generator. Yeah.
Like, why do we use the water?
For here? Don't know if it has. I don't know why actually, like, instead of another liquid.
No, like why do we use it? Before we... Oh, okay.
You were looking at something else in the picture for the last one, was it?
Hmm?
What were you looking at? What were you thinking?
Because like, I didn't know how it's connected to the generator.
Oh yeah, the generator would just be like a separate building, and the steam comes out this along a pipe and goes into the generator. I believe Japan and the EU are working on building a prototype, a practice power plant that uses this process. So in the future, what they imagine is this power plant will be beside, say, a green power plant. So the lasers could be powered by something like wind or solar or whatever. And then that green energy gets multiplied by 10 through the fusion process. So, you know, that really will be 100% clean energy.
Where they get so much hydrogen?
What's that?
Where they get so much hydrogen?
I don't know if it's extracted from seawater. I'm not sure. I think it might come from seawater, but I don't know. I mean, hydrogen is in water, obviously, and there's plenty of that, so. You might have to spend some energy taking the hydrogen out of the water. You can do this in chemistry, using electricity or something, I don't know. You can split the hydrogen out of the water from the oxygen, I think. Yeah. You can, yeah? Yeah. Is it using some electrical current or something? Yeah.
What do you call this?
It's a fusion reactor.
Fusion.
Yeah. It's the future. Isn't that what Iron Man made, wasn't it, or something? First movie? Didn't they have something like this? Yeah. Wasn't it one of these? Maybe, yeah. It's called cold fusion, but I don't understand why the word cold is there, because it's certainly not cold. But you would also hear this called cold fusion. Don't know why. Okay. Right, so we have that. Okay, so there's no formulas or anything to practice on that. So we can just continue down to the next one.